Okay, in this problem, we are going to take a look at a ballistic pendulum. So it's going to involve collisions and energy and momentum. So let's take a look. A student wants to measure the speed of a pellet when it is shot out of his gun. She decides to use the mechanics of a ballistic pendulum, shown below. By measuring the height in which the pendulum swings, she hopes to determine the velocity of the pellet. As shown in part A, a pellet mass m, little m, is shot at a wooden block of mass big M. In part B, the wooden block collides inelastically with the pendulum, and then as shown in C, the pendulum swings up to a height h. We're given the following information: the mass of the wooden block, the mass of the pellet, and the height that the bullet and block rise together. Okay. I really like that this problem has kind of split it up into like what happens first, second, and third for us, because we do want to think about those as kind of three distinct sections of motion. So part A is going to ask us to show that the velocity of the ballistic pendulum right after the collision is 1.44 meters per second. So really that's trying to show right after the collision, so like right here when it goes from B to C. So I'm going to zoom into that B and C. Notice that this isn't actually the collision itself. It's in B, the pellet has already collided with the block, and then in C, it swings upwards because of that bullet's velocity. So because of this, I'm thinking conservation of energy, where you're going to be starting with the kinetic energy of the bullet and the block right after the collision, or I could say at the end of B, and that's going to the gravitational potential energy of the bullet and the block in part C when it's swung all the way up. So that means we're talking 1/2, and I'll use my m plus m, little m plus big M, to represent the bullet inside of the block already. V squared. And that V is right after the collision. And then mgh, but of course we're still talking the bullet and the block, so little m plus big M times g times h. You'll notice that the m's cancel on both sides, which leaves us with v being the square root of 2gh. So plugging in, we have the square root of 2 times 9.81, and we are given h of 10.5 centimeters. That's the same as saying 10.5 times 10 to the negative 2 meters, which all of that should simplify to about 1.435 meters per second, which is pretty close to 1.44 within rounding error. Part B then asks us to calculate the velocity of the bullet right before the impact. So now we're more concerned about the collision itself, what's happening between A and B in that diagram. Now remember that this is an inelastic collision. We were told that this was colliding inelastically. So that really only leaves us one option. Only momentum is conserved in inelastic collisions. So we're going to have to look at the momentum before and the momentum after, knowing that that will be conserved in any type of collision. So before, we have the mass of the bullet times the initial velocity of the bullet. That's what we're trying to calculate. And after, we have the bullet and the block with the final velocity that they move away together. We know the mass of the bullet, and we're looking for the initial, the velocity right before it hits. Over here, the mass of the bullet and the block together moving away at 1.44 meters per second, what we just found in the previous problem. Solving for initial velocity, that comes out to be 198.86 meters per second. Last but not least, part C says determine the energy lost in the collision. So again, this is reminding us this is an inelastic collision. Inelastic collision, momentum is conserved, but energy is not. So that means some of the energy in the system is going to be lost to the surroundings, things like heat, friction. So that means that whatever initial energy we have will equal the final energy plus some that we lost. Again, when I say lost, it's not that it magically disappears. We know that would be a violation of conservation of energy. We just mean that it's lost from the system that we are looking at. What this translates to is the kinetic energy at A of just that bullet flying towards the block goes to the kinetic energy of both of them together at B, flying up to swing in part C. I'll carry down that plus energy lost. That's what we're looking for. So we have 1/2 mu squared is equal to 1/2, and then in part B, our bullet is inside the block. We just found in the previous part the initial velocity of just the bullet. Oops, I think I meant for this to be a capital M. They fly up together at 1.44 meters per second. We're looking for the energy lost. This comes out to be about 61.3 is equal to 0.44 plus energy lost, which means about 60.9 joules of energy is lost in this collision. It was definitely an inelastic collision. So in this problem, we examined a ballistic pendulum where you have a bullet flying into a block and together they move up. We started by looking at just the second half of that, what happened after the collision, looking at conservation of energy to help us. We then switched to focus on the collision itself, remembering that an inelastic collision is where momentum is conserved, but energy is not. So we used conservation of energy to help us find some unknowns, and we also determined how much energy was lost in that collision.